Hi, I'm Nathaniel Chodosh, and I'll be presenting our work reevaluating LiDAR scene flow. What we're looking at here is an in-the-wild car as seen by the LiDAR sensor on an autonomous vehicle. Here we've added the same car as seen a tenth of a second later. We've removed the ego motion of the autonomous vehicle so we can infer from the offset of the two captures that this car is driving forward. In order to succeed at the self-driving task, autonomous vehicles must be able to make similar inferences. Typically, this is approached as a supervised learning, detection, and tracking problem. But there's significant interest in label-free approaches which don't rely on a predefined object taxonomy. This approach is called scene flow, and when done without labels, self-supervised scene flow. The goal of scene flow is to predict a set of vectors like this, where each point in the first point cloud is labeled with a motion vector indicating its displacement into the second point cloud. If we look carefully, we can see that while every vector begins at a green point in the first point cloud, most of them do not end at an orange point in the second. This is because the LiDAR sensor measures a sparse set of points at each sweep, and so the same point generally is not measured twice, meaning there will be no true correspondences between the two captures. This lack of correspondences is one of the challenges that makes estimating even simple linear motion like this difficult. One of the other main challenges is that this motion needs to be detected in large, outdoor scenes where most of the measured points belong to stationary objects. Here we plot background points in green and foreground points in orange. The foreground points generally make up around 15% of each scene, and moving foreground points only around 8%. This means that we need to not only detect the motion in the noisy, correspondenceless motion point clouds on the left, but we also need to do it when 90% of the input consists of what are essentially distractors. These are the two main challenges of scene flow estimation from LiDAR sensors. There's been significant interest in the task of motion estimation from point clouds in the past few years. Here we show just a small selection of the publications in top venues. Despite this interest, the vast majority of these works focus on getting performance gains on datasets which don't actually exhibit the two main challenges we just outlined. We will present an analysis of the problems with these datasets and show that these problems are leading researchers to create scene flow methods that actually perform poorly on real-world data. The most common datasets for scene flow evaluation are Flying Things 3D and stereoKITTI. Both of these datasets were originally intended for 2D optical flow and disparity estimation, and to extend them to 3D scene flow estimation from point clouds, previous works used these labels to lift the 2D annotations into pairs of point clouds with correspondences between them. We claim that there are three main issues with these datasets that together obfuscate the main challenges of real-world scene flow estimation. The first issue with these datasets is that the pairs of point clouds given as input are in perfect one-to-one correspondence. On the left, we show a pair of frames from stereoKITTI plotted together. We can see that every blue point in the first frame has a corresponding red point in the second. We've added a small displacement to the aligned point clouds, since otherwise the points completely overshadow each other. This is of course very different from the example from real data on the right that we already looked at. The second issue is with the amount of dynamic points in each example. As we discussed, real data has a severe class imbalance between moving and static points. However, stereoKITTI has far more foreground and moving points than real data does. We can see this in the bar plot on the left here, where we compare the rates of foreground and moving points in stereoKITTI with those rates as found in real-world data sets from autonomous driving companies. Somewhat paradoxically, this actually makes the stereoKITTI flow estimation task much easier, since methods don't need to deal with as many distracting background points. The final issue also relates to the difficulty of finding moving objects in the scene. The ground truth flow annotations from KITTI were created by manually identifying the moving cards in the scene and then fitting CAD models to them. Correspondences were then extracted from the relative positions of the models in successive frames. In contrast, the background points were created by aggregating multiple LiDAR sweeps and then using the ego motion of the car to assign them flow vectors. The result of this process is that the moving objects end up with a very distinctive sampling pattern that distinguishes them not only from the background, but also from cars that weren't manually identified as moving. As we'll show, this sampling pattern essentially gives away the answer to the problem of finding moving objects in the scene. We show this with a simple experiment where we will train a classifier to segment moving points from the static points. The catch is that this model will not be given access to the second frame of the input, so it can't possibly learn anything about the actual motion in the scene. Additionally, we will only give the model access to a tiny amount of local information. Specifically, the input to our segmentation model will be just the local neighborhood of each point visualized in this red circle. Then, the model will predict the moving static label of the point at the center of this neighborhood. We train our model on 150 ground truth segmentations from stereoKITTI and test on the remaining 50. This is a common split that is used to fine-tune scene flow methods. We can see that this very simple model, which uses no temporal or global information, is easily able to segment the moving objects with high accuracy. On the right, we show an example output, and at the bottom, we give the average results over all of the 50 test examples. Due to the sampling pattern only appearing on cars that actually move, we see that the model is even able to distinguish between parked and moving cars. To recap, we've identified these three problems with current scene flow datasets: the one-to-one correspondence, the unrealistic rate of dynamic points, and the sampling pattern on moving objects in stereoKITTI. We will now analyze how these problems actually affect the types of scene flow methods being published. The analysis is fairly straightforward. We took a set of several recent self-supervised scene flow methods, all of which report results on stereoKITTI. We retrained them on a set of autonomous driving datasets, Argoverse, NuScenes, and Waymo, and then we looked at how the performance on stereoKITTI relates to the performance on real-world data. Here we show the main result of this analysis. On the x-axis, we have the endpoint error of each method on stereoKITTI. We take these numbers from their respective publications. And on the y-axis, we have the endpoint error on the dynamic objects in real-world datasets. Each method is plotted with a different marker, and each dataset is plotted with a different color. For each dataset, we then draw a best fit line relating performance on that dataset to performance on stereoKITTI. We see that performance on each of these datasets is actually negatively correlated with performance on stereoKITTI, indicating that chasing performance gains on these unrealistic datasets is hurting real-world performance. In our full paper, we present more analysis of these results, showing evidence for the effect of each of the aforementioned problems separately, and we also show how a simple non-learning baseline can actually outperform all of these tested methods. Thanks for listening.